let's do a couple of examples to make sure we have a good intuitive understanding of this IV relationship. So let's take, for example, number 1, V is some constant, V naught. Then, hopefully you believe me that I equals 0. So that's the case where we charge up the capacitor. We've left the voltage on for a very long time. We need to do that because these are time-dependent devices. We always have to kind of remind ourselves of history. When we do that, a certain amount of charge Q will build up on the device. We know how much charge Q will be because we know that Q equals CV. So we know that that is a relationship that tells us the charge. And once that charge builds up, and while it built up, there was a little bit of current. But that's in the long past. That's history. So now we're just sitting there. There's a voltage on the capacitor. There's a charge on the capacitor. We could take that capacitor and disconnect it from the circuit. The voltage would stay there, the charge would stay there, and clearly the current would be 0. If the charge isn't changing, it must be the case that the current is 0, because the way you change charge is you pump some current in or out. So that's a nice simple one. Should understand that. What about V is some straight line? Let's just make it some little a, t. It's a function of time. In this case, linearly increasing as a function of time. Well, if I take the derivative of that, then the current equals, looks like C times whatever the slope is. So in that case, we are linearly increasing the voltage. We're ramping the voltage up. As we do that, we find that the current is actually a constant. It might actually be easier to think about that the other way around, because this relationship doesn't tell us what we're controlling and what we're measuring. So let's actually turn it the way around. Let's say we drive in a constant current instead of putting, in this first case, a fixed voltage supply and finding no current. Let's put a fixed current supply and force the current to be constant. When we do that, we see that well, first of all, let's go to here. If the current is constant, then the charge must be building up linearly with time. We're just adding more and more charge. We have to have the charge, Q, is building up in a straight line, and therefore the voltage must be going up in a straight line. So this is just charging up the capacitor. This is like pouring water into a bucket. If you pour the water in at a constant rate, current, you find the amount of water, the charge goes up linearly with time, and the potential energy of that water, there's more and more of it, would also go up linearly with time. So if you understand derivatives, then you can put any function you want in here and find that they relate. Again, this is critically different than a resistor, because we can't ask what's the voltage at some instant in time, only knowing the current at that instant in time. That works fine for a resistor. We have to know the history. We have to know the slope of the voltage, how it's changing in time to get the current. Instantaneous values don't tell us everything we need to know. This device has history, and the history is recorded in the amount of charge that's built up on it. That's something the resistor doesn't have, this internal state of charge, and that's what makes this device different.